Hello, everyone. Good day and good time wherever you are. This is another AM Smart webinar number 10, and this is a specific webinar dedicated to the topic of 4D printing. And I have two great speakers today. I would like to introduce them first and a little bit tell about their background, and then we can start with the presentation. The first speaker, Dr. Zolfagharian, he's from Deakin University, Australia. He has very nice background and record in 4D printing. The topic he chose for today is robotic materials 4D printing, and he's going to give us some information about his previous work. The second speaker, Giulia Scalet from University of Pavia, Italy, and she also has very great background in 4D printing and shape memory polymers, and has established also her own laboratory there at the University of Pavia. The title of her presentation is about 4D printed polymer with programmable shape memory effects, about the modeling, testing, and applications. Here is the rules, and we have usually 30 minutes for each speaker, and then you can follow with question and answer if you want. And the best way that you can ask your question, you can drop your message in the chat box, and even is fine if you do it during the presentation. In the end of the presentation, we will ask the question from the presenter. And if you have any other comments, feel free to contact the presenter even after this webinar. So having said that, I would like to give the floor to my colleague, Ali Zolfagharian. Ali, please go ahead.
Thank you, Mehrshad. Let me share my screen. Good. Thank you, Mehrshad, and hello, everyone. And my topic today is about robotic materials 4D printing. And I am from Deakin University School of Engineering. In the picture, you can see our additive manufacturing lab. And a bit of information about the Deakin University, which is located on the west of the Melbourne, the campus of the Warrenpons, Warrnambool, further on the western part of the Victoria, and also Waterfront, that is in Geelong. We have recently opened our engineering school in Burwood, that is on the east of the Melbourne, all in Victoria State, in southeast of Australia. So let me start with a brief definition of the 4D printing. We define 4D printing as additive manufacturing of smart materials which change their shapes, properties, or even color in response to external stimuli such as heat, humidity, electricity, or magnetic field. So using that, we can save more time, energy, and post-processing, and coming up with the robots or actuators or sensors that could be manufactured using additive manufacturing with the intention to be run in one step. In our lab, we have some equipment related to 3D printing and bioprinting and characterization in terms of 4D printings and soft robotics, which you can see here, range of the printers, mainly polymers and bioprinters that I'm working in my lab, and also working on vibration tests, characterization, and soft robotic using the Conzer and MATLAB interfaces. Not far from the first day that 4D printing was introduced by Skylar Tippett, and first paper of that was published by Jerry Key in Georgia University, and also Skylar from the MIT and his TED Talk. In 2016, I have started working on 4D printing in our lab with different applications from morphing structures, structural elements, its application in sports and medical devices, soft robotics, and very recently on vibration, absorption, and isolation. From the beginning, with the collaboration with the colleagues and also with the focus we focus on how we can come up with the programming of the shape morphing that could be used for the soft robotics and robotic application using the 4D printing. A range of the programming approach have been introduced. For example, you could see on the right is a pattern-driven 4D printing that with drawing different patterns on printing different patterns on the pre-strained polystyrene sheet. We could achieve that bending and then control the bending using the 3D printing specific parameters. And then we come up with the cold programming that we use the printing process parameters like the velocity and the temperature of the nozzle and bed to print something and then apply the loading in the room temperature or below the TG, and then applying the TG, we could harness some sort of the bending. And the most genuine approach that we come up with that 4D printing programming is the hot programming, that during the manufacturing, using the printing process parameters, we could embed the amount of the bending or morphing we could harness after the printing with applying the stimuli such as magnetic field, heat, electricity, or so on to harness the bending. For example, you could see on the bottom image using the different velocity of the nozzle, we could come up with functionally graded materials with harnessing different amount of the bending after applying the heat. Coming up with these methods, then we could work on different case studies and different projects related to the 4D printing in direction of soft actuators and soft robotics. Another material that has some benefits for 4D printing is the hydrogels, because they are processable and also they are stimuli responsive. They could be swirled and deswirled, and also they could be stimuli with different methods and stimulants like the heat, humidity, electricity, and so on. We work on polyelectrode hydrogels and then developed some actuators based on the osmotic pressure and Donan effect, that with changing the polarity of the electricity, change the direction of the actuation and control the swirling and deswirling. They have some application in biomedical cells manipulation and also as a sensors in aquaculture and so on. And further, we could even come up with the more sophisticated type of those actuators with the combination of both bioprinter and commercial FDM. We come up with some parallel robot that they have more precise actuation and they can carry more payload. And also, we have included some fibers into the hydrogel during the printing, and you could see some sort of the morphing shapes like this saddle shape or this twisting morphing that we could achieve all under the same volume. So with the same volume or of the materials or actuators, you could achieve different bending or morphing shapes using only 3D printing or 4D printing parameters, that with changing the fiber direction either as a parallel or with the different angles, we could work on the modeling of this morphing and show the effects of the fiber direction that could be achieved during the 4D printing for hydrogel. Very recently, one of my PhD students succeeded to develop vascular tissue engineering and show the application of the 4D printing in that. So the idea was using the silk cocoon as a biocompatible material to be used for soling and desoling that we could control the amount of the bending as part of that 4D printing for the application like the vascular structure that you could see here. And a further application of the 4D printing as soft sensors were presented as well. We could use the hydrogels as a capacitive sensors, and then working on the modeling of the hydrogel, given that they are incompressible, and then relate that incompressible amount of the soling and desoling to the electricity as a sensor. And then also we work on the variable strain sensor with the self-healing and conductivity, as you could see after cutting into the pieces, and the pieces can come back to each other based on the self-healing characteristic of the hydrogels with the still high conductivity to be used as a sensor for biomedical application. One of my main interests in 4D printing is soft robotics, that coming up a combination of the materials and design for using the additive manufacturing and particularly 4D printing for developing soft robot in one run. Again, based on the programming methods that I explained earlier, like the code programming or shape programming, we succeeded to develop different type of the grippers with the carrying different material and payload and sizes, as you could see here in the soft robotic grippers. And also inspired by the nature, we could embed some sort of the torsional spring as a hinge into that finger and soft grippers. We also work on the thermal suppression as another project of one of my PhD students, and we succeeded to suppress the vibration of in the range of the frequency of the person with the Parkinson disease. I will talk about that later. And non-assembly mechanisms were printed in one run using the 3D printing for soft robotic application too. Not all the materials has the characteristic of being responsive in response to some external stimuli. That makes the 4D printing quite challenging. So we came up with the idea of heterogeneous 4D printing, that we brought other stimuli responsive material or some sort of actuators like the shape memory alloy or carbon fibers for that as the external part that could be used for transferring the heat, so that we can use the 4D printing programming in integration with those external actuators like the shape memory alloy or the heaters that is a flexible carbon fiber. And then we succeeded to show their application for like the flexible joint in some soft robotic application for reducing the vibration of the endpoint of this flexible joint that you could see on the right picture, or as a gripper with the variable stiffness using the shape memory alloy. Other direction of the 4D printing soft robotic is soft pneumatic actuators. Is one of the most well-known application of the 3D printing, and also we could name it as a 4D printing because the pressurized air or a pneumatic stimuli that could be used based on the design of the actuators that you could conduct during the printing. You can get a different amount of the bending and the force at the tip point of this sort of the actuators. And also we have used the design aspect of the additive manufacturing and 3D printing that make the flexibility in the design and individualized design of that is the advantage of the 3D printing. We could develop a personalized spoon that we name it like spoon 4PD. That 4PD is for Parkinson disease patients, that based on the measurements that you could have from the hand and the palm of the hand and specific measurements that you could have for an individual, you could design a specific spoon relying on tune mass damping. The tune mass damping is one very popular application, popular direction for the reducing the vibration application. And then we use that one for reducing the vibration of the endpoint of the spoon based on the design that we consider during the 3D printing for this specific application for Parkinson's disease people. Also, we work on the silicon. One of the very interesting material in the soft robotic is silicon, because it has quite high elasticity, and then they could be mixed with other materials that they have their different amount of their rigidity is silicon. So we use the two elastomer silicon, that is the EcoFlex A and B. One of the issue in 3D printing of the silicon is the mixing of these two part silicon. And then we come up with some design of the static mixture that is not commercially available, in order to come up with the mixing of two part A and B. As you could see here in the picture, from top to bottom, you could see how the mixing will occur using this specific design of the static mixture based on the computational fluid dynamics. And then we printed our printer using the syringe pump for that silicon printing, and we could develop some soft materials, some soft products for actuation, as well as some biomedical applications. Using that silicon 3D printing, we could work on AI-based 4D printing for human-robot interaction. We developed the different silicon modules in different shapes, and then embedded the sensors like the accelerators at different location of those products. And then you could see that with the different touch between the human and the modules, like the slapping or tickling, using the AI, we could successfully distinguish between different interaction, human and robot. And again, leveraging on using the silicon, we mix the silicon with the ethanol, and that the mixture of these two leads to some sort of the actuation upon the heating, because the ethanol reach to the boiling temperature and will be evaporated, but its bubble will be entrapped into the silicon, and then that leads to some sort of the swelling after heating up when it reached to the boiling temperature. So we used this characteristic and then added the flexible fiber as a heater into the silicon, and then printed that in the rotary printer, as you could see with here on the top left video. And then we use them for the vibration reduction, and with changing the stiffness of that joints in robotic application. And further, we work on the biostable mechanism inspired by the Venus flytrap plant with the same material. And also we showed the application of that in the parallel robot that you could see on the top right video, how with using the some sort of the string wrapping around the silicon, we could confine is motion to the linear motion after the expansion. And also recently in our lab, we started working on using the biostable mechanism that could be 3D printed and then have some application in the soft robotic application, particularly for vibration. And with after trial of several designs, we could come up with the designs that achieve the biostability. One of the issue here was the boundary conditions, that because of the defects that occur during the 3D printing, we needed to come up with a very optimized way for 3D printing of this sort of the biostable mechanism. And then few of this design reached to that biostability that was there. And then we show the application of this biostability with uh, stacking this biostable mechanism into each other. As you could see, we could have some sort of the displacement that was needed, and with changing of this displacement manually, it was not like a 4D at this stage, but it has a potential for 4D printing for the future direction. The proof of concept was to show how we can reduce the amount of the vibration with changing the location of the mass in some flexible structure that could be potential of the 4D printing. And we also work with another PhD student on developing sort of flexible materials that we name it metamaterials, because we could achieve the desired force displacement with making a lattice of those materials, again inspired by the nature from this sort of the grasshopper type of the mechanism we developed. And then with using the lump parameter, we were able to print and then model that. Our main contribution to this work was developing this sort of the biostable mechanism in the MATLAB based on the pseudo rigid beam modeling, and then connecting those beam model and using the springs to come up with this sort of the compliant mechanism. And then we could use AI, artificial intelligence, and particularly machine learning and surrogate neural network in order to be able to estimate the behavior of the mechanism with changing the design with thousands or millions of the data we could achieve after validation with the experimental results. And again, we could stack this sort of the biostable mechanism in a series, as you could see here, and with changing the location of this biostability at different location, that, for example, the bottom one, the number 3 from the bottom, or number 5, which one would be in what state, with changing the state of this series of the biostability mechanism, we could come up with our desirable stiffness. That desirable stiffness then shown the application in terms of the vibration reduction, as you could see here in a phantom model of the hand. We applied those biostable mechanism that was totally 3D printed, and we could have different amount of the stiffness with changing that biostability. And then you could see the difference that on the top, those spheres all remain in the spoon, but at the bottom, with changing that stiffness, they are dropping with the application of tremor suppression in the Parkinson's disease patient. And further on the bottom right, you can see we show the potential. We see the potential of the 4D printing. We come up with the biostability that with changing the temperature could change the state. That you could see those mechanisms on the bottom side, and these are our future direction of the work for applying on the same mechanism for vibration suppression with changing the state of the stability. And also, we are working on the metamaterials inverse design using PEN. PEN stands for physically enhanced neural network. So we use the physical simulation and models as a constraint or loss factor in the neural network or machine learning. So using that, we could have some advantage of reducing the amount of the data for training of neural network. And also we catch or capture the nonlinearity that is involved in the physical rules. And then we use some sort of the optimization in order to make some stochastic or searching algorithm for covering lots of possible scenarios for the force displacement. And we start with a very simple, like as you could see, like a pi and f shape, and then we connect them together. And again, using that physical enhanced neural network, and in using the MATLAB, all AI and modeling and finite element under the one platform that is a MATLAB here is performed. And we could come up with the several scenarios that we wanted the desired behavior of our metamaterials. As you could see here, from the inverse design, we give to our algorithm, we input the algorithm the desired performance or stiffness that we want, and we could come up with the final design based on the different stiffness and the force displacement behavior that could be achieved. And you could see here in the video. And just last slide, that was almost all that I had in terms of research. There are some sort of statistics about the 4D printing. As you could see from the recent Scopus search, I found that 4D printing shows quite promising publications that is well spread, leading with China and US, and then followed by India, UK, Australia, and other Asian and European countries. And we have very recently developed, established, and founded our 4D printing journal that that Mehrshad and also Giulia are part of our editorial boards. And you're welcome to submit your recent paper on the 4D printing to this journal. Is a hybrid journal, both open access and subscription. And also I refer you to look at our 4D printing roadmap for introducing yourself to 4D printing, if not much so far. And we have our 4D printing societies that with the different members from the university that all around the world are part of that. Since 2022, we started working on the 4D printing all together on different applications. And we have our annual conference that we recently had our conference jointly with A-Star in Singapore, and 2026 will be announced soon. And thank you for your time and your attention to the presentation. Thanks.
Thank you very much, Ali. It was very interesting and, let's say, on time. There are a couple of questions drop in the chat. I can read it for you. The first question from Maysam asks you, what is the density range of as printed samples? How much do the structural defects affect performance?
Yeah, thanks. Definitely, I don't remember that the stiffness range. Sorry for that, but I can come back to you or refer to the papers that is published there. But for the defects, I can assure you that there are very critical factors. I think the question was related to that bistability, I believe. We had, because for the bistable mechanism, there are the boundary condition and the force, and there are two things that are very important. The boundary condition will be affected directly by the defect that could be happened during the printing, but this could be optimized. Now we have also progress in terms of the printer that we have and the materials that we have. So compared to what we were like 3 years ago, now, for example, like the bamboo printers coming, they're quite fast and quite well in terms of the printing. So these all help that we could move toward the getting the better results in terms of the bistability. And at the end, we came up to the stage that we almost got what was desired between the simulation and our experiment.
Very good. Go to the other question. Mohammed, thank you for your presentation, and ask, what is the normal amount of a spring back for a program for the printed structure over the time? For example, after 1 hour, 1 day, 1 week, and longer time.
It all depends on the material that you use. Even the PLA from the different companies are supplied with a different amount of the properties. And so that's something that you need to do the experiment. And that's why I think from the spring back, I'm not sure whether they're referring to shape fixity. In the 4D printing, we name that shape fixity. And then we have shape recovery. And I'm not sure which one they mentioned, but all of them should be first experimented and tested. And based on that, you go for your design and modeling. Because based on the different material, the TG, and then you need to do the DMA, dynamic mechanical analysis, and so on, and then will inform and then go to the design.
Okay, very good. I see some people are still writing, but for sake of time, let's move on. Thank you, Ali, very much for your presentation. Now we want to continue with the second presenter, Dr. Giulia Scalet from University of Pavia. I mentioned at the beginning. Giulia, the floor is yours. Go ahead, please.
Yeah, thanks. So let me share my screen. Okay. Can you see my presentation?
Yeah,
also?
Very well.
Okay, also the laser the pointer?
Yes, yes.
Okay, perfect. So I can start. Good afternoon, everybody. So first of all, thanks a lot to Mehrshad for this kind of invitation. I am really happy to be here today. As Mehrshad already said, I come from the University of Pavia in Italy, so it is just a few words. It is in the north of Italy, quite close to Milan. And also my lab is the Laboratory of Programmable Materials and Structure is located on the scientific campus that is a little bit out of the city center. So our lab, as the name suggests, works on programmable material and structure. So we work from different points of view. In fact, my team is quite multidisciplinary. We start from the processing, in particular with bioprinting and printing approaches, material characterization, modeling and computation, and also a small lab dedicated to biological characterization. So you can find all our equipment, events and news on our website. So today I want to focus on programmable materials. So just as a brief introduction, what programmable materials are. They are materials that, as the name suggests, are really dynamic. They can be programmed in order to adapt to different situation, application need. And this is a very simple example of a sample, a thin sort of thin sample that can adapt its form, its shape to match a different type of surfaces. Obviously, this is just an example, but you can think to open your mind and program materials in order to adapt different physical properties, functionalities, such as in the literature, you can find a lot of examples on shape programming, stiffness, Poisson ratio, color, adhesion properties. So there are a lot of work in this sense, and obviously it depends on your needs. And also to design programmable material, there are a lot of work behind. So there are three main ingredients that you can use in order to design a material in order to make it programmable. You can work and play with the base materials that can be different, the stimulus, so its application, or also the type of stimulus that is not only mechanical, but it can be also a thermal, magnetic, and so on, and also the architecture. So you can play on specific geometries, such as the classical examples are metamaterials, origami, kirigami, or bio-inspired design. So it is you have a lot of examples, and today I'm gonna talk about a programmable system made of shape memory polymers. So shape memory polymers, as the name suggests, are soft material able to remember their initial shape. Almost all polymers feature the so-called one-way shape memory effect. This is a very simple effect that can be schematically represented in this way, where you start from an initial permanent shape, you apply a specific programming history in order to fix a temporary shape, and after the application of an external stimulus, you can recover the initial shape. And as you can see in this picture, the thermal stimulus is the most used one. The only thing is that, as the name suggests, this is one way, so you cannot go back to the temporary shape once the recovery is completed. This is why researchers work on other type of shape memory polymers. There are polymers that can feature the multiple shape memory effect, where essentially the idea is very similar. But in this case, you have more than one programming step where you can fix a different temporary shape, and after that, the recovery is sequential. So you can program the different shape in order to have a programmable shape changes. And again, this is very important to achieve programmability, but again, this is one way. So once you have recovered the final shape, you cannot go back to the temporary shape, but you have to start again all the programming step. And this is why we are working a lot on two-way shape memory effect. The idea is here is to play with the thermal and heating cycle in order to move from one shape to another one in a reversible way. So we have the additional feature of programmability and reversibility. These effects are very promising because you can couple the shape memory polymers with the 4D printing approaches. So I will not enter again into the detail and advantages of 4D printing, but this is very advantageous for application. In fact, there are a lot of applications you can find in the current literature, and also we had an additional application that is very, very challenging, that is the use of this material for cancer engineering. So to use this material as a scaffold in order to to manufacture some dynamic in vitro models that can be in a simple way mimic the real dynamicity and programmability of the tumor microenvironment. And for all of this application, programmability is essential. This is why we decided to work on this type of feature. There are a lot of challenges behind, so there are experimental, so from the practical point of view, theoretical, numerical, because we have to find essentially the optimal polymer for our application, and this polymer is highly nonlinear, and there are a lot of phenomena behind to tune its behavior. So in particular, today I want to talk about our recent result, focusing both on the one-way, multiple-way, and two-way shape memory effect in order to achieve a programmable shape memory system. In particular, I will show you some results concerning these key ingredients highlighted in the red boxes in order to achieve programmability. So let's start just from the beginning. Few words about the shape memory polymers. Again, the shape memory effect, as you have already understood, is the result of this programming history plus the recovery ability. And obviously, the architecture of the polymer plays a fundamental role because it can be synthesized in order to tune the response of the polymer based on your needs. Essentially, we have a domain that is responsible of this effect that can be where essentially there is this transition temperature that can be a melting or a gas transition temperature, where you can essentially that is responsible of this behavior, and a net point where you that can be cross-link physical or chemical, and is responsible of this shape memory fixity and recovery. So in particular, we have worked on different type of polymers. So let's start from those based on the glass transition temperature. And in particular, let's see how to obtain programmable shape changes using the one-way shape memory effect. So as you have already understood, the basic one-way shape memory effect is not suitable for programmability. You can see this very simple example on which we have worked some years ago. You print this structure, you fix this deformed temporary shape, and upon light irradiation, in this case, because the material is composed of gold nanoparticles, you can obtain through indirect heating the initial shape. So this is a very simple example, but it is not programmable. This is why we have working on programmability by using two materials. So a structure made of two polymers with different chemical composition, and this different chemical composition led to different glass transition temperature with the same amount of gold nanoparticles. And in this case, this is the initial shape. This is the deformed temporary shape. Upon light irradiation, you can achieve a sequential shape change. So it is possible, again, using just one-way shape memory polymers, but with multiple polymers within the same structure. And you can also play, again, with the different polymers, but with the same chemical composition, so the same glass transition temperature, but you can use a different content of gold nanoparticles in order to achieve a differential heating, so a different heating upon light irradiation that allow to achieve again sequential shape changes and sequential shape recovery upon light irradiation. So you have different approaches that you can exploit in order to achieve programmability also with the one-way shape memory effect. You can model. So I'm a structural mechanics. So this is my starting point from my PhD. So we have worked a lot on constitutive modeling, and you can also propose this constitutive model, in particular those based on phase transition, to describe and support this design stage. The idea of this approach is to introduce particular specific phase variable, the scalar or also tensorial, in order to describe all the inelastic effect and phase within the material, in order to describe the final shape memory of behavior of the structure. So I will not enter into detail of all the equation. In this case, we have a rubbery and a glassy phase, since the polymer is based on a glass transition, and you can introduce a specific tensorial phase variable to describe all the inelastic deformation that are associated to the different shape memory effect. And you can obtain a model, in this case, that is able to describe a different effect, not only the basic one, but also an incomplete shape memory behavior. So you can define the Helmholtz free energy as classical done in the literature with a mixture of rules, and you can derive in a thermodynamic consistent framework all the constitutive equation. So you can implement into numerical code. We did it in the Abacus for the Abacus software, and you can support this prediction, the behavior of this structure by numerical simulation, and the comparison show very good result. The main problem we face with, for example, this structure, but also other structure, is, as you can see, you start from a permanent shape and you have to deform the structure to a temporary shape. So you have to apply, first of all, a mechanical deformation under isothermal condition at the beginning. And this is the first step of the programming step. And this is, let's say, challenging from the numerical point of view because you don't know a priori the boundary condition to apply in order to get the right target temporary shape. So it is essentially a sort of trial and error approach also for this numerical simulation, because you start to apply a load, a boundary condition, a values, but at the end it could be not the right one, so you have to change a lot. And this is especially true for very complex structure. And this is why we try to support this step by coupling this final element simulation, so with our constitutive model, with mesh morphing. So mesh morphing helps us in order to skip this trial and error approach and to achieve the target temporary shape that should be usually known based on images technique, or also if you have a target application, you know that your target shape, and you can apply this mesh morphing technique in order to avoid this trial and error approach based on final elements. And we validate also for this case of this flower, and the results show a good accuracy compared to the traditional approach. And now let's go to the second part. Let's try to understand how to make a programmable structure using the multiple shape memory effect. We did it using a commercial polymer. So I'm honest, we were very lucky because we found this multiple shape memory effect in a commercial resin for the 3D printer by Formlab, the stereolithography one. This resin is very advantageous because it has a broad glass transition temperature that is a prerequisite for the so-called temporary memory effect. What is this effect is very similar to the multiple shape memory effect. So we have a permanent shape, different programming step, and this recover that is sequential, but the main important feature is that the material remember the deformation temperature, so the temperature at which it was programmed, and this recovery take place essentially at this deformation temperature. And so we play with this material. We coupled also with some, as I said, architecture, such as this program, this auxetics. So we were able to achieve a different sequential out of plane and in plane shape changes using this resin, and this allows us to achieve programmable shape changes based on our need. We also verify through numerical simulation, in this case with some simple rheological model, the classical generalized Maxer one, in order to support this design step. And you can also play with this effect in order to achieve a more complex structure. This is a very simple example of a self-locking clamp. So essentially you have this is the printed one. This is the deformed shape during the first programming step. This is the second shape at the second programming step. And finally, we can recover sequentially this deformed shape up to the initial one in a sequential way. So in this allow to close the clamp. And we support this simulation, this experiment also with the numerical simulation. So let's go to the last part of this call, that is on two-way memory effect. So in particular, this is a typical feature of polymers based on the melting transition temperature. This is the main activity we are now conducting, and is focusing on multi-phase semicrystalline network. These are a specific type of material that are able to feature this kind of effect. And essentially, in a general word, this material is composed of one or more polymers. Each polymer has its own crystalline and amorphous domain, and so it has its own crystalline temperature, crystallization temperature and melting temperature, and you can pass from one state to another by cooling and heating cycle. And this is essential in order to activate this two-way memory effect. So this is an example of the two-way memory effect for a network made of just one polymer, and you can see that it can express this two-way memory effect under stress-driven and stress-free condition. So it is very advanced for different type of application, and you can see that there is this reversible passage between two deformed shape upon cooling and heating cycle, passing through these melting and crystallization temperatures. And the same happens if we consider, for example, network made of two copolymers. It is the same thing, but we have more polymers and so more crystallization and more melting temperature in order to achieve also reversible but also sequential shape changes. We printed for the first time these materials with an extrusion-based approach. So this is, you can refer, I will not enter into the detail of the chemistry of the material. This is for a PCl-based semicrystalline network. So it is just one polymer, but this technique can be extended also to other type of networks. And we use extrusion base with UV cross-linking during printing. And we were able to manufacture different type of actuator that are based on the one-way memory effect and two-way memory effect with different design. So this technique was also very interesting because allowed us also to obtain self-folding structure upon immersion in solvent, thanks to the material gradient within the thickness. So in particular, we use again this network, and we print different layers of this network, of this material, using different cross-linking parameters. And this allows us to obtain a material gradient along the thickness that bends upon immersion in the solvent. And this bending can be also supported with the classical, very easy beam theory, starting from the Timoshenko theory, that can show essentially good result in terms of accuracy. Finally, let's just focus also on the modeling. So this is a very important part because these multi-phase crystalline networks are not modeled in the literature. So we propose this first model that allow to take into account all the possible conditions, so different polymers within this network with a different inelastic deformation contribution, and that are responsible of this two-way memory effect under both applied stress and stress-free condition. So again, we introduce phase variable, scalar, and tensorial, and we derive again, as I described before, all the constitutive equation evolution law for the phase variable, in particular using the experimental evidences we observe. So it is a purely phenomenological model. And the results are very, very good in the sense that we validated the model for a different type of network, both on homopolymers and the copolymer networks, also for different ratio between the polymers. So the model is able to catch well, despite this very complex behavior, the material shape memory performance. So let me conclude this talk. So I have shown you different type of approaches in order to achieve a shape memory system with the programmable capabilities, in particular exploiting different type of shape memory effect. So essentially for the one-way effect, this is not possible, but you can play with the different polymers within the same structure in order to achieve a programmable behavior. But again, it is not reversible. And this effect is mostly used for biomedical, pharmaceutical application. Multiple shape memory effect is very useful to achieve this programmable shape changes, but again, it is not reversible, and the two-way shape memory effect is able to achieve with also copolymers or more polymers this reversibility and programmable shape changes. So we have worked a lot. We have still some work that we will publish in the close future about also tuning these material properties going behind the classical chemical composition. So let me conclude by thanking also my team. So in particular, Matteo, Lorenzo, Nicolette, and Paul, and also all the past students and members of the team, and all my collaborators. So it is a very long-lasting collaborator with Stefano, Maurizio, Daniele, and Massimo, and also other new collaborations that I established within my grant. And I have also, if you are interested in our activity, you can refer to my website, and also we organize some scientific seminars. And thanks a lot to everybody for your attention.
Thank you very much, Giulia. Thank you. Very nice presentation and organized for different type of shape memory. I very much enjoyed that. I see some question here. The first question I would ask you is from Thomas. First, thank both of you for your presentation. I think his first and second question, they are relevant to each other. And let me read the second one. Have you used in your recent work a polymer with properties similar to nitinol, shape memory alloys?
Polymer with nitinol, you mean some thermal properties or mechanical properties?
For example, shape recovery and mechanical properties, yeah.
Yeah, it is a very different behavior. So yeah, I have not compared now nitinol with shape memory polymers. So we have our objective is to make these polymers, in particular the two-way shape memory one, for suitable for biomedical applications. So our objective now is to catch the thermal ranges typical for biomedical application, biological in particular application, and obviously the mechanical properties are really different because they are soft materials. So in our case, we are lucky because for shape memory polymers for tissue engineering, cancer engineering, we don't need a lot of forces, actuation forces, recovery stresses, and so on. So they are quite limited if compared with nitinol, for example.
Very good. The second question from Mohammed asking you which one of the following method has better fixation ratio: hot programming with low programming loading time 1 hour, or cold forming with high programming loading time 1 day? It's a very specific question.
Yeah, very specific. So to now is the for the fixity. It depends on the polymer again. We work mostly on hot programming. So, for example, this semi-crystalline network are really performant in terms of shape fixity and shape recovery. So also the fixity depends on the presence of on the macromolecular architecture, so on the presence of cross-link, the crystalline domain. So it depends on the polymer, not only on just the programming step.
Yeah, I agree. All right. I also had some question, but I skip it for now, just for sake of the time. Thank you very much, both of you, Julia and Ali. It was very, very interesting talk. And what I'm going to do, like the other webinars, we will share the video with all audience later, and also for the bigger community, if they miss this webinar, they can watch the video later. And again, like always, I appreciate also the attendance, also for attending this specific meeting and webinar. And you can follow our future webinars, also video from the previous webinar on the website and LinkedIn page. Yeah, that's all from my side. Thank you both, and thank you everyone, and have a very good day.